Hi, everybody. I wanted to make a couple of videos to show you some of the principles that we've been talking about with electricity. I know you've got the test that you've been working on, and you've been working on trying to make sure that works well, but at the same time feeding you new information about electricity and electric fields and electric force and potential energy and capacitors and breakdown. And so, you need a few examples of the kinds of problems that now I'm going to be expecting you to do. So that's what this is all about. So let's start with electric force. Let's just deal with a simple problem that's going to test our So let's see. Let's say we have a central charge, which is, and most central charges are very small, so we'll always have, most of the time in electricity work, we're going to have things with prefixes, so you just have to understand that. So let's say we're going to have something that is 5 microcoulombs, and we have a field charge of 20 microcoulombs. And let's say that they're separated by a distance of, let's make it 2.5 meters. And the question is, what's the force electric between these two? All right. And now here's where you need to understand that we have a couple of different kinds of problems only that we're going to be working with. This is to simplify things, but you have to be aware that there are these two different kinds of problems that we're going to be working with. One kind of problem is going to be a set of charged particles. Like this problem, we have two charged particles, a QC and a QF. The other kind of a problem is one where we're going to have a lot of charged particles. And most of the time, that's going to be a capacitor problem. Most of the time when we talk about a lot of charged particles, we're going to have them on the plates of a capacitor, and then that puts into play a whole different set of equations. The concepts are the same. There's still an electric force, and there's still an electric field. There's still a distance between things, but they apply to a capacitor as opposed to two point charges. That's the way we talk about it in physics. In the first example I'm showing here, the set of charged particles, those are point charges. We can imagine that the QC and the QF are just 2 points in space, whereas if we have a lot of charged particles and they're put on a plate, well, now they can't be thought of as points in space because the charges are distributed across an entire plate, and we have to take that geometry into account. And so that kind of a problem, we've limited our exposure to that kind of a problem to parallel plate capacitors. There are other geometries we could do, but we're not going to. So anyway, here we have a set of charged particles, and so we know the equation for that. It's Coulomb's law. Coulomb's law says the force electric is the electric constant QC times QF over R squared. So that's clearly what we need to do. We have the information. You can do this kind of a thing, and actually I would encourage this. I know QC, I know QF, I know R, and I know the electric constant. And so I can calculate the electric force, and in this problem, that's exactly what I'm trying to calculate. That's the question. So there's just a way, just putting down what you know, the given, again, the given, and what you're trying to find, and then look for some relationships and some principles that relate these things. So this is just going to be a plug and chug kind of a problem. Just put the numbers in, crunch the numbers, and come up with the answer. So let's do that. Let's say that the force electric is 9 times 10 to the 9. And that has units. I'll put those here. That's Newton meters squared per Coulomb squared. Times 5 times 10 to the minus 6 coulombs, because that's a micro. Okay. This, the 10 to the minus 6, that's the number that is equivalent to a micro, a prefix. So I have a prefix of a micro up here, and I'm just going to replace that with the number that it's equivalent to. You find that on the chart in the front of your book. And then I've converted from microcoulombs to coulombs. And then I've got 20 times 10 to the minus 6 coulombs. And then I have to divide that whole thing by the 2.5 meters squared. And now let's check. I've got square meters here, and I've got square meters here. That matches. I've got a coulomb here and a coulomb here. That's a coulomb squared. There's a coulomb squared there in my electric constant. And I'm going to end up with newtons as my result, and that's appropriate set of units for the force electric. So before I do all the number crunching, I make sure my units match and I don't have any units mismatches. So here we go. Let's put these numbers into our calculator here. And we've got 9. Where's my exponent? There it is. 9e9 times 5e minus 6. No, that wasn't right. Let's clear that. 9e9 times 5e 6. And I want to make sure the 6 is a negative. No. Nope. That's not going to do it either. All right, hang on here a minute. All right, let's try this again. 9e9, that's 9 times 10 to the 9, times 5e6. This is the key I was looking for. Change sign to negative 6. All right, times 20e6. Change the 6 to a negative. That's the numerator, and then I've got to divide by 2.5 squared is 0.144. Newtons. And I did it again. I turned off my calculator, which I did not want to do. Let's just get that back. There we go. All right. So there's a simple example of using Coulomb's law. Okay. Now, let's just build on this problem. Let's just ask the question now. And let me make a diagram here just to make this. So here's QC. And here's QF. And the distance between them is R. And I'm going to ask the question now, what's the E field at the position of QF? Okay, so here's the physics that's going on here. The physics is saying we just calculated that there's a force at a distance. Why is there a force in it? We just calculated there's a force on this field charge, and nothing's touching it, so it's a force at a distance. Why is that possible? Because this central charge is creating an electric field that's everywhere in space, and that means there's an electric field right here where the charge QF is located. And because that charge is in a field, it's going to feel a force. And we just calculated that force, that Coulomb force. That's exactly what we just calculated up here. That's the amount of force that it's going to feel. And now the question is it attractive force or is it negative force? Well, look at our two charges. Our two charges are both positive. They're both positive. And if they're both positive, we know that the forces are repulsion. And so there's going to be an electric force right here pushing the field charge away from the central charge. And we just calculated that that's going to be 0.144 newtons. But we can now ask, okay, that's the force. What's the field located right here? What's the field? Well, that's a different question. And we have, if you recall, we have two equations for electric field. We have an equation 1 that says electric field E is the electric force divided by QF. And we had another equation for electric field that said electric field was K electric QC over R squared. And if you recall, electric field tells me the amount of force, amount of electric force on a normal charge. And a normal charge is +1 Coulomb. Well, I don't have +1 Coulomb. My field charge is 20 microcoulombs. That's okay. Electric field is normalized. It tells me what if I had +1 Coulomb at this location, how much force would it feel? That's what electric field tells me. And both of these equations tell me that. Look, here. If I actually have 20 microcoulombs as the field charge, and that field charge is feeling a force of 0.144 newtons. If I divide, think of it this way, the electric force that I have is 0.144, watch this, we'll just write it out. The electric force, I'm going to make some units here. 0.144 newtons per 20 microcoulombs. That's how much force there is. There's 0.144 newtons per or for 20 microcoulombs. Now, when we report force, we normally don't put the coulombs in there. I'm adding them in to make a point, a pedagogical point. This problem, I hope you can see that in this problem, it makes sense to say 0.144 newtons per 20 microcoulombs. That's the situation. But look at these units. These are not units of force. These are units of electric field. Electric field has units of newtons per coulomb. Well, if I actually do this math, 0.144 newtons divided by 20 times 10 to the minus 6, 7,200 newtons per, and now I've done the math, so all I have is coulombs in the denominator because I've divided by the 20 microcoulombs. And I don't normally show it, but I could show a 1 coulomb in the denominator. Well, now I've got 7,200 newtons per 1 coulomb. Well, that's electric field. This is electric field. That's equation 1. That is equation 1. Take the force electric and divide by the charge that that force is acting on, and I have the correct units for electric field. So if I had a 1 coulomb charge at the position of QF, it would feel 7,200 newtons of force. I don't actually have 1 coulomb, I have 20 microcoulombs, so of course it feels less force. How much less? It feels 0.144 newtons per coulomb. All right, so that's our equation. That's the relationship between electric field and electric force. All right, now, here, let me just make this, because somebody's going to write this down and it's going to cause you trouble. This is not a real equation that you want to memorize. This is not. Electric force does not equal newtons divided by coulombs. I did this for pedagogical reasons to show the relationship between electric field and electric force in a particular problem. This is the equation. What I was trying to show you was another way of thinking about the relationship, the ratio of force divided by charge. That's the point I'm trying to get across. This calculation that we did is force divided by charge. That's electric field. All right. But we should get the same answer if we use this equation, our second equation, because we have all the information we need for that as well. Let's take a look at that. Let's actually do that calculation. All right. So we should have E equals K electric, and then Q central was, let me remember, 5 microcoulombs. 5 microcoulombs over 2.5 meters squared. So let's just do the calculation and see what that gives us. So that's 9E9 times 5E6 minus, that's the 5 microcoulombs. Right, so there's the numerator, and then I've got to divide by 2.5 equals, and then again divide by 2.5, that's like squaring, and I get 7,200, which is exactly what I should get. And the units are newtons per coulomb. Now look, this equation is so close to Coulomb's law. If I wanted to make this equation into Coulomb's law, all I would need to do would be to put a QF up here, right? Look at these two equations. Look at, and I'm sure you've noticed this, we've pointed it out before. Look at this equation, and look at this equation. The only difference is that we're missing a QF in the electric field equation. But what I'm going to tell you is you can think of it not as missing, but instead of as missing, as being a particular value, and that value is 1 coulomb. If I imagine that there's a field charge of 1 coulomb, I'll get the same result. It'll be 7,200 newtons, right? And that'll be the amount of force on a normal charge. Well, that's the definition of electric field, the amount of force on a normal charge. Okay, so there are some simple equations, just applying our Coulomb's law equations and our electric field equations. Now, the next level of complication comes when I have more than one central charge. So let's just do two central charges, okay? We'll just do two central charges. So let's say I have a QC1 there. I have a QC2 there. And I have a QF up there. Okay? And I've got them in a geometry. Now, as soon as you get away from two objects, two charges, you've got to define some kind of geometry. A third particle is going to create some kind of a geometry. Here the geometry is a simple isosceles triangle. Right? All sides are the same. Right? So this is R, this is R equals 0.6 meters. We'll just make it 0.6 meters all the way around. 0.6 meters and R equals 0.6 meters. So all three sides are 0.6 meters. And now I'm telling you, by the labels that I've got drawn, that this is a central charge and this is a central charge. What that means is that QC1 is creating a field, QC2 is creating a field, QF, here's a point that maybe has been confusing to you. QF also creates a field, but that's not the way we think. We think of QF as feeling the other two fields. The field charge is the charge that feels a force because there are fields created by other charges, central charges. If I were to ask the question another way, I could choose to make this a central charge. If I was not interested in figuring out the force on this charge, and instead I wanted to figure out the force on this charge, then this charge would become the QF. And this would become a QC. It all depends on where we're looking. It's the context. Remember, context is key. It's true in literature, it's true in theology. Context is key, it's true in physics. You got to know what your context is. In this question, I'm asking about the charge that's located at the top of the triangle. That's the charge I want to find the force on. And when I do that, I'm going to necessarily think of that charge as the field charge. So let's put some values in here. Okay, let's say that this is plus 6 millicoulombs. And let's make this minus 9 millicoulombs. And let's make this minus 2 millicoulombs. Okay? So those are the sizes of our charges. And this is my physical diagram. Okay? Remember physical diagrams? This is my physical diagram. And now we're asked for force electric on QF. That's what we want. The force electric on QF equals what? And immediately you should think, well, I have two central charges. Each one of those is going to produce a force on the field charge. So they must be asking me for the net. They may not say it, but I need to understand from the way the problem is set up and the way the information is given that they're looking for the net electric force on QF. Well, net force, that's something we've been doing for weeks. So I need to add vectors. Oh, as soon as I need to add vectors, I had better make some context lines. So there's my context. And let's say that this is positive and this is positive. Just pick the standard stuff. Okay, this is a force vector diagram. All right, it's not a graph. I know this can also look like axes on a graph, but this is not what we're doing. We're doing a force vector diagram. We put arrows on this. So here's an arrow. First of all, let's make a little sketch here. Here's where we've got to put a couple of pieces of information together. Let's look at QC1 first. QC1 is positive. QF is negative. That means they attract. So that means that there's going to be a force down this way. There's a force of attraction. QF is going to be pulled directly towards QC1 because they're opposite in charge. Now, let's concentrate on QC2. This is a negative charge. That means that it's going to repel the field charge because it's also negative. So there's going to be a repulsion up like that, away from QC2, directly away. So we bring that information over here and we draw okay. So I'm using my physical diagram to help inform me about my vector diagram. This is force, and we're going to call this F1, and this is going to be force F2. And here's my reasoning behind the way I'm naming things. This name here is going to be telling me that this is the electric force on the field charge, that's the little f, and it's the electric force on the field charge due to the central charge number 1. And by the same token, this is going to be the electric force on the field charge due to central charge 2. Okay? And now I need to do a little bit of geometry stuff. I know that this is 60 degrees, this is 60 degrees, this is 60 degrees. But I'm going to make a little construction here for myself. Watch this. If I just add a little line here straight down, and maybe I even drag it up a little bit, let's see. I hope you can see, and I hope it makes sense, that, oh, I did that wrong, didn't I? Yeah, I'm not even looking at my own diagrams correctly. So let me swing this guy down here. There, that's the way that ought to be. Okay, there we go. So this is FF1, okay? And now hopefully you can see this is 30 degrees. So this is 30 degrees. And this up here will be 30 degrees. So that this up here will be 30 degrees. So a little construction line drawn on my physical diagram can help me transfer information about angles correctly over to my vector diagram. And now we've got the setup. And I just need to know these forces. Well, I can write these equations. I can say F1 is K electric, QC1 times QF over r squared. And FF2 is K electric QC2 QF over r squared. See, this is where your name comes in handy. If you name things correctly, it really helps. I need my field charge and I need my central charge 2. So that's what appears here. There's central charge 2, there's my field charge. I need my field charge and I need my central charge 1. Well, that's what I have, QC1 and field charge. Those are what go in there. So now I can calculate those. All right, so let's get our calculator here. Clear this. So I need 9E9 times QC1. That's 6 millicoulombs. That's 6E3 minus. That's a millicoulomb. Times 2E6 minus. That's the numerator. And then I'm going to divide by 0.6, divide by 0.6, and then again equals, and then divide by 0.6. That's dividing by 0.6 twice. So there's 300 newtons. So this is 300 newtons. And if we do that over on this other one over here, we can, all the numbers are the same. Let's see, do I dare do this? No, we'll just do it again. We'll just do the whole thing again. Try and get clever, but that's not worth it. 9E9 times QC2 was 9 millicoulombs. 9E3 minus times 2 millicoulombs, right? 2E3 minus equals, divide by 0.6 equals, divide by 0.6 equals. That doesn't seem right. That doesn't seem right. What did I do wrong here? Something's not right. Let's try this again. 9. Let me just make it so I can see all the numbers here. 9E9 times 9E3 minus times 2E3 minus, divide by 0.6 squared equals, no, 450,000. Okay, so the 300 can't be right. So we'll just have to go back and do that. So this is 450,000 newtons, and I must have pressed the wrong key here. Let's go back and see 9E9, and let me pull these down so I can see the numbers again. 9E9 times 6E3 minus times 2E3 minus divided by 0.6 squared equals 300,000. There we go. Somehow I missed that before. 300,000 newtons. Okay. All right. So I've got my lengths of my vectors now. Okay. And then I just used Coulomb's law to get it. And now I'm going to make my boxes. Remember the way we always do these vector problems. I have off-axis vectors, so I'm going to make the boxes from the tips of the arrows, draw lines parallel to the axis lines. Let me do it correctly here. So I have a new vector there, I have a new vector there, I have a new vector there, and I have a new vector there. These are all components, so let me give them names that are appropriate. So this is f, f2y, and this is f, f2x, and this is f, f1x, and this is f, f1y. And you notice that when I put the numbers into the calculator, I didn't worry too much about whether there was a minus sign, minus 9 millicoulombs. The minus is just direction, and I've already taken direction into account in my diagram, so I don't need to be worried about taking direction into account in my calculations. I already know which way vectors are pointing. So don't get hung up on the minus signs. You're just trying to find the length of a vector, and the length of a vector is always a positive number. Okay, that may solve some problems for you. All right, so now I just have to do my trig. I have to do my trig. So if I were to say f, f1x equals f, f1, and now this is going to be here now. Let's take a look. Got to decide whether it's sine or cosine. Those of you who are trig people, you'll immediately say cosine, and you'd be wrong. f1x is up here. It's this vector here. That's the same as the side here of this box, and that's opposite my 30 degrees. And so it's going to be sine. It's going to be sine. So this is going to be the sine of 30 degrees. And f, f1y is going to be f, f1 cosine of 30 degrees. So we can calculate those things. Let's do that, right? So let's get our calculator here. So FF1 is the 300,000. So 300,000 times sine, no, let's clear that. Let's do this. 30 sine, there we go, times, easy, 300, typed it wrong. 300,000. 150,000. And let's do 30, and we'll do cosine times 300,000. $259,807. 259,807. Actually, we'll round it up. 808. You keep more digits. I'm going to round off. No. I hope I remembered that right. 257, I thought it was. 259. Well, since it's not showing here anymore, I'm going to calculate it again. So let's do 30. Oh, it's clear. 30 cosine times, no, 30 cosine times 300,000, 259,807, and then let's just let me just keep it the way it is. 259,807.6. So we'll just do 808. That's fine. So I did remember it correctly. Okay. Newtons. And then we can say f2x equals, and this will be f2 times sine of 30 degrees, and f2y equals f2 times cosine 30 degrees. And let's just make sure that's right. Yep. the x component is going to be sine. That's right. Okay. So this is going to be 225. And this one's going to be, let's see, $450,000. So we got 30 cosine times 450,000 is 389,711. 389,711. 389,711 newtons. You keep all the digits. I get to round off. Okay, and now we have to figure out the net. Well, we have all the components, and we can start now to put this together. And we'll notice that I have two vectors along the vertical axis. I have ff2y and ff1y. They have to be added, and it's really going to be a subtraction because they point in opposite directions. And then I've got two along the horizontal direction, ff2x and ff1x. They point in the same direction, so I'm going to add those two together. Right? So let's see. Let's do the x's first. So let's do this first and this first. So we'll get f net x equals ff1x plus ff2x. And that's going to be 375,000 newtons, and that's going to be left. Okay, 375,000 newtons to the left. And then we're going to do the y and the y. So let's do that, and let's do that, and that little indication there for my eye. And f net y is going to be, so let's see, up was positive, so that was ff2y, so that's going to be 389,711 minus the ff1y was down, so that was going to be 259,808. That's right. ff1 was down. That's right. Okay, so that's the negative one. Okay, so let's do this. I got the 389,711 there. That's already here. Minus the 259,808. 129,903. Right? And this is down. Oh, I'm sorry. This is up. This is up. Okay? ff2 was bigger than ff2y was bigger than ff1y. So up wins. All right? So now, this is kind of the summary of everything, right there. So let's make a new diagram, because now I need to add those two vectors together, right? I need to add those two vectors together. So I'm going to make a vertical axis, a horizontal axis, and I'm going to pick a vector here, and I have left and up okay, and I've tried to show the lengths in some proportion here. So this is f net y, and this is f net x. Okay? And I need to add those together, and I do that by making the box using those two vectors as my markers for the boxes. And then the vector that goes between those is my f net vector. Here's f net. And I need to figure out this angle here, theta. We'll call that theta. So f net, just do Pythagoras. So I'm going to do f net x squared plus f net y squared. So I have the 129,903. I've already got that. I'm going to square it plus the 375 squared equals, and then square root, and I get 396,863. 396,863. 396,863. Okay. That's the length of the vector, and now I have to figure out the angle of the vector, and I've defined the angle to be in this direction here. Now usually in MathXL I'll tell you which angle I want from what line to what line, but here I've defined it as from the negative x-axis up to the vector, the net vector. And here's where I need to do a little bit of inverse trig. So here's what I'm going to do. I'm going to use tangent. I'm going to say the tangent of theta is f net y opposite over f net x adjacent. Opposite over adjacent. So theta, which I don't know, which is what tells me I have to do an inverse tangent of f net y over f net x. Okay, and so I can just do that. Let's do this here. Okay, so let's clear this. So we're going to say f net y. That was the 903 divided by 375,000. That's that. And now I need to do the inverse tangent of that. And I get 19.1 degrees. So remember, a vector has two components. It has a length and it has a direction. And now I've defined both. And that's the complete answer. So that's the that is the calculation of the electric force, the net electric force. Okay. Now, just like we've done previously, I can ask, what's the electric field at that point? So let's go back to the beginning of the problem. Now I can shift my focus in the question and say, what's the electric field at this point? Not the electric force on this particular charge. I want to know the electric field there. And if you recall the old trick, electric field is force electric divided by QF. Or we'll just be consistent here, little QF. So this is going to be the 396, 863 newtons divided by 2 millicoulombs. because that was the field charge. It's 2 millicoulombs. It was negative. Notice I'm not putting the negative in because that's only direction information. I don't care about direction. I have other ways of figuring out direction. I just put in the magnitude or the size of the charge, 2 millicoulombs. I just need the numbers to crunch the numbers. Okay, and so here I'm going to get, clear this. We go 396. 863 divided by 2E3 negative. That's 2 millicoulombs. And I'm going to get 198 million 431,500. 431,500 newtons per coulomb. That's a big electric field. That's a huge electric field. Okay? And the question is, what direction does it point? Okay? Well, now we remember what electric field tells me. Electric field tells me the force on a normal charge. Remember, there's a 1 coulomb here, and you should remember that there's a positive 1 coulomb in the denominator of an electric field because a normal charge is plus 1 coulomb. And that means that if I go and look at my original problem, my field charge was negative. See, my original charge was negative. And I end up with a force going out this way. A positive charge would feel a force 180 degrees opposite. It would be down and to the right instead of up and to the left. And as a matter of fact, it's just that simple. I just make 180 degrees and this is the same theta, okay? But it's down and to the right because an electric field is the force on a positive charge. A positive charge, okay? Now, this is one way to do it. This is our one equation for electric field, right? This is our one equation for electric field. Our other equation for electric field was almost like this. It was almost this equation, except QF is 1, so we don't show QF in the equation. It's just KEL QC over R squared. That's electric field. And all that's done is that's replaced my actual QF with a normal charge, 1 coulomb. I could go through the exact same process I just went through with the vectors and pointing in different directions. And if I just replaced the field charge with 1 coulomb instead of minus 2 millicoulombs, I'd go through the same process of adding vectors and net vectors and some inverse trig, and I'd get the same answer. I'd get the same answer. So you can approach it either way. Okay, you can approach it either way. All right. So there's some problems that should hopefully be helpful. Let's do some potential energy problems. So let's say we have QC, and we've got here a QF. And let's say, in addition, that this distance is R1, and there's another distance that's shorter, that's R2. And let's say we want to we'll do our first problem. Move QF from R1 to R2. What's the change in the potential energy if I move QF from R1 to R2? Okay, so let's put some numbers in here. Let's say that QC is 5 microcoulombs. QF is 1 microcoulomb. R1 is 1.5 meters, and R2 is 0.9 meters. Okay, so those are my numbers. And we want to know the change in PE. Okay, so remember, delta PE is PE at the final minus PE at the initial. Okay? Well, in our case, we're moving from R1 to R2, so the final is 2, so it's PE2 minus PE1. Right? And if you remember, our calculus result, PE, was K electric QC QF over R. Okay? And both our charges are positive. Okay? That's the way we've got it. And so we can say, we'll just calculate these. PE1 is something. Let's figure out what PE1 is. Okay? And we'll go here so I can see my numbers. Clear. And I can do 9E9 times 5E6 minus times 1E6 minus divided by, and I'm doing PE1, so it's 1.5. 1.5. 0.3. 0.3 joules. And PE2 is 9E9 times 5E6 minus times 1E6 minus divided by 0.9 equals 0.5. And both of these are positive potential energies. And so delta PE is equal to 0.2 joules. And it's positive. It's positive. It's 0.5 minus 0.3. It's positive. Another way to think of it is I'm moving against laziness. These are two positive charges. They want to go further apart, and I'm making them go closer together. Laziness lowers potential energy. Against laziness raises potential energy. So we're raising the potential energy by 0.2 joules. Okay? So there's an example. We've calculated potential energy. We've calculated change in potential energy. Let's see. Let's do some capacitor problems. All right? Let's do a capacitor problem here. So let's do some capacitor plates. Let's see. I want to add. I want to insert a shape. Yep. Okay. So here we go. Here's a capacitor plate. Here's a capacitor plate. and I've got positive plate here. I've got negative plate here. I've got, let's say I've got a battery here, positive, negative. Okay, and let's say that we have, let's say 36 volts on this battery, and let's say that the distance between plates is 0.01 meters, a centimeter. Okay, how's that? All right, a couple of things here that we can do. First things first. We know that we have separated charges. We have a bunch of positive charges on a parallel plate and a bunch of negative charges on a negative plate. And when we separate charges, we create electric field. And so the electric field points in the direction that a normal charge would want to go. A normal charge is positive, so it's going to want to go down. So this is our electric field. Okay? And we want to figure out what that electric field is. How much is that electric field? What is E? Okay? And as soon as I ask that question, what's E? I should think, oh, a 1 Coulomb field charge. Because electric field tells me the normal force. It's the amount of force on a normal amount of charge. Okay? So a normal charge is plus 1 Coulomb. So I'm going to imagine a plus 1 Coulomb charge. I'm going to imagine that there is a plus 1 Coulomb charge at the top plate, and I'm going to let it go, and it's going to travel down to the negative plate. It's going to be attracted to the negative plate. And this is plus 1 Coulomb. Okay? And by the time it gets from the positive plate to the negative plate, its potential energy is going to have to go down. That's the force at a distance. It wants to get to lower potential energy. The negative plate for a positive charge is lower potential energy. We'll call that 0 PE. So it's going to change its potential energy by moving from the top plate to the bottom plate. Well, that's exactly what voltage tells me. Remember, voltage is normalized PE. So 36 volts equals delta PE over QF. All right, well, we've got a QF of 1. So delta PE equals 36 joules. A 1 Coulomb charge, if it moves from the positive plate to the negative plate, is going to go through a potential energy change of 36 joules. Okay, that's going to be important because this is the area under a force versus distance graph, because that's what I've taught you to do for PE. PE is the area under a graph. Well, there's force, right? We're looking for electric field. An electric field is force on a normal charge. I have a normal charge because I imagined putting one in here for simplicity. And the electric field is the measure of the force on that charge. Well, here's a relationship between the force on the charge and a PE number that I now know, 36 joules. So here I'm going to just draw a graph. Now this is a graph, not a vector diagram. It gets confusing. All right, so this is a force electric versus distance graph. So this is newtons, and this is meters. And the graph is going to be a straight line. It's a nice simple graph because we're dealing with a parallel plate capacitor, and the force between the plates of a capacitor is uniform, which means it's just a straight line graph, nice and simple. And the distance here is 0.01 meters. And this area is 36 joules. And I know the width now, and so I should be able to figure out the height, right? Because 36 joules equals force electric times 0.01 meters. And I should be able to solve that simple equation. Force electric is 36 joules divided by 0.01 meters, and that's going to be equal to 3,600 newtons. So the electric field is 3,600 newtons per coulomb. Now remember, there's a +1 in front of that C. I had a +1 coulomb charge that I put in here, imagining it to be there. And I solved the problem with that as my field charge because that's the simplest thing to do when I'm working with normalized equations, normalized concepts and ideas. And so I know the electric field is 3,600 newtons per coulomb. Okay, so there's the electric field between the plates of a capacitor. Now, let's go back. No, we won't go back. We'll just carry forward. How about that? So we got the same setup here. Got the same thing. 0.01 meters. It's the same capacitor. These are our positive plate. This is our negative plate. And we got the 36-volt battery. Right, and we know that we've got an electric field here. We're just going to borrow the ideas. (3,600 newtons per coulomb). So now we're going to put in here a positive charge, and it's going to be 2 microcoulombs. And I want to figure out how much its potential energy changes when it goes down to the bottom of the plate. Okay, when it goes 0.01 meters, right? I want to know what that's going to be. Well, I can do two things. First we'll do it the long way, and then we'll do it the short way, okay? And the long way would be to make a graph again.
Call from 5713-861806.
This is force electric versus distance graph. This is newtons. This is meters. This is 0.01. And force electric is equal to, remember our equation. Well, let's just do this. E times QF. Remember, our equation that we had, that we've used a number of times now, is force electric over QF is electric field. If I just do the algebra on this, I get this equation. This is not a new equation. This is just algebra on this equation. All right? So here I know the electric field, and I know the field charge, and I can calculate the force electric very easily. All right? So I've got 3,600 times 2E6 minus equals 0.0072 newtons. So that's what's here, 0.0072 newtons. And the area equals the change in PE. So if I were to calculate and multiply, I would get 0.000072 joules. Or delta PE, the change in PE is negative because the PE is going down because the particle is going in the direction it wants to go, so it must be lowering its PE. So it's a negative change in PE. And we've got 1, 2, 3, 4, 5, 6. We've got 72 microjoules. That's the change in the PE. Okay. So here are, a set of problems that kind of roll a number of things that we've talked about in the past week together. Hopefully these will help you with the homeworks that are coming up. Hopefully these kind of start making the ideas connect to each other. And I admit that times, I present a principle. Sometimes it's hard to see how it applies to some previous principles. That's certainly something that I would expect you to try and look for. Look for ways that new principles link with old principles. Those are great questions to ask in class. Anyway, hope these are helpful, and let me know. Let me know if you need to see some additional kinds of problems. Ask at the beginning of class. I always give you a chance to ask then. Thanks, everybody. Have a good evening.